We talked for one whole lecture about resistive forces. I still remember the number of that lecture. It was number 12, because it's the one lecture that I worked on it more than on any other, with the help of my graduate student, Dave Pooley, who did these wonderful calculations, these numerical solutions. And so let's talk a little bit about the resistive forces. If an object moves through a medium, air or a liquid, there is a resistive force which always opposes the velocity. It has two terms, k1 times v, this is the speed, this is always positive, plus k2 times v squared, and this is the unit vector of the velocity. So it's always opposing the velocity. So this is the magnitude of the resistive force. We dealt exclusively with spheres, remember? And we did some cute experiments. For spheres, k1 equals c1 times r, and k2 equals c2 times r squared. And we did some experiments with corn syrup. And this was a syrup for which c1 was approximately 160, and c2 was about 1.2 × 10 to the third kilograms per cubic meters. I always remember the units of this, because that's always density. In fact, it's always a little smaller than the actual density of the liquid of the syrup itself. This is a more complicated unit, but you can figure that one out for yourself. And so we had ball bearings from 1/8 of an inch diameter to 1/4 of an inch, and we dropped them in the Cairo syrup. If we take the one for now, which is 1/4 of an inch diameter, then the mass of that one is about 0.1 grams. We knew the density of steel, and so you can figure out the mass. Just take my word for it. And so the question now is, if this ball bearing starts to fall, what is the speed that it will achieve? Well, in the beginning, there is only mg on that ball, and a teeny weeny little resistive force. As the speed builds up, the resistive force will grow, and there comes a time that it's equal to mg, and then the object will not be accelerated anymore, and it will have what we call the terminal velocity. And so what are the conditions for terminal velocity? That this term equals mg. In other words, that c1 r v plus c2 r squared v squared becomes equal to mg. And when that's the case, then we have reached the terminal velocity. Well, this is a quadratic equation in v of t. You know c1, you know c2, you know the radius of these ball bearings, you know the mass of the ball bearings, so you can solve for the terminal velocity. You will get two solutions. It's a quadratic equation. One will be non-physical, you will see, so you keep the one that is physical. But if you did that, that would be a silly thing to do. And the reason why that would be silly is that I claim that this term, which by the way we call the pressure term, that this term can be completely ignored compared to this term, which we call the viscous term. How do we know that that pressure term can be ignored? Well, let's first ask the question, when is the viscous term and the pressure term the same? For what velocity? So forget for now that here are t's. We just want to know that this term is the same as this term. That will be the case when the velocity, which we call the critical velocity, equals c1 divided by c2 times r. It's very easy to show that this term is then exactly identical to that one. There's nothing critical about that number. Really, it's a wrong name, critical velocity, but we give it that name. It simply means that the two terms are equal. That's all it means, nothing else. If you calculate for a 1/4 inch diameter steel ball bearing, you can calculate r, you will find that the critical velocity is about 100 miles per hour. And we know very well there is no way when you drop a 1/4 inch ball bearing into this syrup that it's going to come anywhere near that. So the speed will remain way below 100 miles per hour, and therefore, this is a term that will dominate, and this term can be completely ignored. And if that term can be ignored, you can see that immediately the terminal velocity is going to be mg divided by c1r. And that, by the way, for our quarter-inch ball bearing, turns out to be something like 2 centimeters per second. Many, many orders of magnitude lower than the 100 miles per hour, which was the critical velocity. What we did is we measured the times for these ball bearings to fall over a distance of 4 centimeters. And if you know the time to go a distance of 4 centimeters, you know the terminal velocity. And we know the mass of the ball bearing, we know the radii of the ball bearing, we know C1. No, we didn't know C1. I just wanted to point out to you that you can measure C1 that way. You measure the speed, you know R, you know M, you measure C1. And that's what I did before the lecture that morning. That's how I came up with that number 160. Otherwise, I wouldn't have known. C1 is extremely temperature dependent. In fact, it even changed between classes. If the temperature goes up, the value for C1 goes down. So that's the way you can measure the value for C1.